Okay. So today we're going to actually do the exact same topics we did last time, but finishing them up this time. We're going to talk about power electronics first, finishing that up. I'm not going to have any more demos because this took quite a while apparently last time. But we're going to talk about inverters and DC-DC converters. Just briefly there, we won't go into as much detail or sort of look at kind of what they do to real power signals, but we're going to talk about them kind of conceptually, understand what they're actually doing. And then we'll talk about power flow, the majority of this lecture. Couple administrative notes. I am going to, by the end of today, email everyone some comments on their proposals. I didn't quite finish writing all those this morning, but by the end of the day, you'll all get comments on your proposals. Some of you will get suggestions on possible mergers. So I think a few of you had one-person groups. In that case, I might suggest some people that you might want to merge with. But it's only if sort of it makes sense given the projects themselves. We prefer people do it in groups. It just means you have a chance to work with people. But if it doesn't make sense, then that's fine too. The other thing, I sent out an email this morning, but the homework is going to be actually due next Thursday, not next Tuesday. The reason for this is that I actually was going to hold office hours tomorrow, but I can't because there was a change of schedule where not change of schedule, but I had not realized we actually had going to be off-site tomorrow, so I won't be able to do that. But because of that, we can't have extra office hours the days before, so I'm just going to go ahead and push that homework to be due on next Thursday. And in that case, we'll have the office hours on Monday as usual, and then longer ones on Wednesday. So we have the extended office hours before the homework's due. I think that was it for administrative questions. Were there any questions about the logistics of the homeworks or particular proposal? By any chance? Okay. Then in that case, I will jump in. I guess people seem to be more people just watching the videos, I guess, as opposed to doing the coming. But I guess that's a good thing, maybe in some sense. All right. So last time we talked about power electronics, right? And in particular, we sort of had really visual demonstrations of what exactly is going on inside of those things. There's one question too, which the person asked is not here, unfortunately, but someone asked whether or not LED lighting used the actual LEDs in the rectifier itself. And I thought they didn't, but I wasn't quite sure. I wanted to check. So they don't. LED lighting will always have almost all the things I ever saw had normal rectifiers in there. And the reason for that is that when you're trying to optimize a system, like a little piece of electronics, you probably should either optimize for outputting light very efficiently or blocking flow of current very efficiently for as low cost as you can, right? And trying to do something that does both these things isn't that efficient. And you really want your actual LEDs to really be over here on the load side so that they're always getting the same direction of current flowing through them, so you can give a sort of a nice smooth amount of light being released. And you want your rectifier to be the ones here that kind of prevent the flow of current. So the LEDs in general will, in fact, have their own rectifier. I think that was all I was going to say. I think there are other questions about how that all worked and the power electronic side in terms of rectifiers, but more generally in terms of how these things really work in devices. Any questions there? Okay. As a last comment, part of the value of all this, I mean, this is kind of considering electronics or electrical systems at a very small scale, right? We're going to shift today to thinking about them in a much bigger scale in terms of actual grid level systems. But a lot of the usefulness of these types of ideas is that if you understand what power is doing at the home level, that actually can be very useful for analysis at the home level, right? So if you want to detect what kind of devices are on in a home, for example, which is something that I've done a fair amount of work in, it can really help to know exactly how these nonlinear circuit elements are going to distort the current signals. You can actually use that as a signal of what kind of devices are actually on, right? So if a light bulb and a monitor use the same amount of power in total wattage, you could still tell which was which if you were actually able to look at the actual AC waveforms, because the monitor would typically have this sort of shape like a rectifier where you had these little spikes of current draw and then zero at other times. So it can be very useful for kind of understanding what's going on at the building or home level for analyzing that power. These kind of techniques can really be helpful here. So just to mention the two other things that are the two other kind of conversion methods that I talked about last time. Remember, transformers were how you go from AC to AC at different voltages. Rectifiers were how you go from AC to DC. The third one here is inverters. And again, inverters sometimes refer to more than just these, but I'm going to use inverters just to talk about systems that convert from DC to AC. So you have some direct current signal. How do you actually make that something like an alternating current signal? And I think actually what we're going to just talk about right now is a pretty rudimentary way of doing this. In practice, you want to do a lot more kind of nice things because this, as you'll see, creates a pretty blocky, not very sinusoidal-like signal, at least in its standard form. But the basic idea here is that we're going to see this new circuit element for the first time here, which is a switch. And switches are very, very important. Not actually so much, well, a little bit in inverters certainly, but also in DC-DC converters. So almost all DC power sources, in addition to the rectifier, also have some way of regulating output voltage, which, as we'll see in a second, that uses switches very, very predominantly. And in fact, when you start doing things like switching at high frequencies, where you're actually toggling a switch, 10,000 times a second, or even more, 30,000 times a second, this actually introduces a lot of noise on the electrical line. And there's been some really cool work actually about looking at that noise to try to figure out what's going on, what kind of devices are on, by actually looking at the noise they inject into the voltage signal from these switches. That's an aside. If anyone's interested about that, you can come talk to me. It's a very sort of recent and cool piece of work. But the basic idea here is that what we have is we have a switch element. And fundamentally, a switch is just something that can be, it's just like a light switch, right? It's either open or closed. When it's open, current cannot flow through it. When it's closed, current can flow through it. And while a light switch is sort of how we think about this maybe intuitively, of course, you don't want something that will take that long. You don't want a mechanical switch there that will take that long to actually turn on and off, and have issues of when you have moving parts 10,000 times a second, opening and closing. That would not be very good. You wouldn't want to do that in practice. So the way they're actually implemented in practice are with solid-state electronics. So mainly transistors and things like MOSFETs are the things that actually implement these switches. They essentially are digital elements that, when you put a voltage on them, they are open, and when you take that voltage off, they are closed, or vice versa. Really, you sort of they essentially have three. They're a very, very simple diagram here. Don't take this too literally. But essentially, a MOSFET looks like 3 wires going into it. So if you ever see those little things, they look like this, right? They have like 3 wires, and they have this little thing here. This is a MOSFET, or it's a FET in general, but or a transistor in general, but MOSFETs often look like this. And usually what it is there's a source and a drain, right? So a source and a drain. So current can flow this way. Current can flow this way through it, but there's also one called a gate here. And if this voltage is different, so basically if you apply a voltage to this gate here, and a low voltage, then current can flow. If you don't apply the voltage, current cannot flow this way. So essentially that acts as sort of a switch, right? Because we can control sort of small amounts of voltage very easily, like from a computer, right? You just basically have something that generates a signal where the voltage is going on and off. And then this you apply very little voltage to, and then this allows a lot of current to flow through this when this is on, and otherwise do it when it's off. This is not the symbol in a circuit diagram how these things look like. There are all sorts of crazy symbols. They have things like I can't even remember what these are, but they have things like arrows here, and there'll be things like this for directional MOSFETs, stuff like this. But we weren't going to go into that at all. But just be aware that when you see those things in a circuit diagram, those are almost always essentially a switch, at least in power electronics. They're used for logic in computers. So in computers, you will use them to do things like addition and carry out logical operations. But in power electronics, they're mainly being used as switches. So you essentially control how frequently they turn on and off, and that controls resulting power output. But again, we're not going to talk at all about MOSFETs or those things in this class. But as an example of what you can do with these switches, one very simple example is to build an inverter. An inverter is something which, as I said before, in our context, we'll talk about it converting DC power to AC power. So imagine a simple circuit like this, right? This is called an H-bridge inverter because the thing there looks like an H in some sense, I guess it does. But essentially, it's composed of 4 switches, and you toggle diagonal switches on and off. So at one point, these 2 will be on, and at one point, these 2 will be on. So at one point, these 2 will be closed, these will be open. Another point, these will be closed, and these will be open. And it's pretty intuitive what's happening here, right? This is a DC source, but if this one and this one are closed, current will flow this way through the circuit, right? If this one and this one are closed, current will flow this way through the circuit, so it will flow the opposite way through that resistor here, through that load. And if you just plot what this looks like, if you were to say hook up some logic to make these switches open and close, again, in opposite pairs diagonally, and you want some other sort of smoothing stuff here to kind of make this so you're not being, you don't rely too much on exact synchronization here, but you can get pretty close to that. But if you look, if you open and close these diagonal switches, what you'll see is this square wave pattern, right? Because at some point, what the voltage looks like through this is that the voltage drop looks like that, positive here and negative here. And then when the other ones are closed, it'll be positive here and negative there. And so the voltage signal is just kind of this, you can call it AC, right? It's alternating current is what goes through here. It's not what we think of as a sinusoidal wave, but by opening and closing these things, you created a alternating current pattern through that resistor. And it really is this simple, the H-bridge inverter and the basic step. I mean, you think of things that you would want to be more complex, right, to create AC current, but really the basic design can really be this simple. Now, to get something that looks even close to sinusoidal here, you want to smooth this signal a little bit. And you can do that by things like adding capacitors, or by actually switching these things much more rapidly, but at kind of different cycles. So maybe this isn't, these 2, when they're closed, they aren't quite always closed. You have them open a little while and close a little while, and you have a capacitor that can store charge when it's, so that when they're open, there's still some charge going through that. Basically, by timing these switches right, and by adding capacitors here, you can get something that looks very much like an actual sinusoidal waveform. In fact, you can get, for all intents and purposes, a sinusoidal waveform. So this is not typically how AC power is generated in the grid level, right? Because we have generators that just work as AC generators, I remember, and they just generate AC naturally by those rotating magnets. But there is more and more transmission of DC power, both for devices like you might have in, I mean, all electronic devices for the most part use DC. If you want some alternating current at a very low voltage, maybe you could do something like this inside of a system, say to power a motor. Sometimes motors work better with AC power. And there is more and more usage of DC transmission in the grid now. So DC has some advantages now that we know how to do things like convert from AC to DC and DC to AC at high voltages. Remember, we couldn't really do that back when DC and AC were invented, so we liked AC power because we could do the transformers pretty easily. Now we can do them both ways with these things like inverters and DC converters. We'll talk about in a second. So at this point, it's good to know, this is all we're going to say about inverters here, but it's just good to know that we can, in fact, by using these switches here, convert from DC to AC power. Any questions about this? I'm not going to have any more demos of this, unfortunately. They just, if you could, and maybe this will actually be a homework assignment. I haven't put it in yet in problem set 3, but maybe in problem set 3 you'll look at some QUX simulations of power electronics. That would actually be a good thing to do a little bit of. So for now, that's all I'm going to say about it. You can simulate this in the same software as we were talking about before. It all looks like what you expect, but we won't get into that too much here in class. So the last thing I want to talk about is, and again, very, very briefly, is the final step, right? We did AC to AC, different voltages, AC to DC, DC to AC. Let's talk about now converting DC to DC, but changing the voltage in a DC system. And this also is going to use switches. So just like the H-bridge inverter, the way you can transform voltage, I guess it's actually a very different system than the H-bridge inverter, but the way you convert between different voltages are through these switching electronics. And in fact, all those power sources I was showing you before, they all have this element too. They all have a DC-DC converter in them to maintain, or almost all of them will at least, to maintain an output voltage that is very steady. One thing about the grid, about grid power, is that it does vary somewhat. So we say that the grid is 120 volts, but it'll vary anywhere between maybe, I usually see a little bit more than 120 actually. I usually see it around 120 to 125 or so volts RMS, that is. So having a peak voltage that varies correspondingly. And electronics, though, really do want a very constant amount of voltage supplied to them. They do things like use voltage for logic, right? So they're actually using this voltage to switch on and off very frequently, kind of like switching, but doing it to actually control logic. And if you look at the specs for most electronics, they actually do need a very specific voltage input. So almost all the devices you'll see there have, in addition to a rectifier, they also have a DC-DC converter in them. And there are two types that that are the most common to hear about, and they're called buck converters and boost converters. And there are all sorts of other ones as well, but we won't talk about the other ones as well. There's also buck boost converters and things like this that do both those things, but someone's called like a cuck converter that also is a buck boost converter. But anyway, we won't worry about that. The idea of the buck converter is that we want to transform DC to a lower DC voltage. So we have a voltage source with DC, say it's 10 volts, and we want this load to act as if it has 5 volts hooked up to it. And we use this system. And it takes a little bit of a while to realize why exactly this does what it does. But essentially, the buck converter is actually somewhat intuitive. So we have a switch here, right? Then we have an inductor, a capacitor, and we have a diode too. So really throwing in everything we've seen, right? These are almost all the elements. This is a resistor. This is every single element we've seen so far coming all together in this buck converter. But the idea is, well, if this was just always closed, this switch here, right? The inverter, I mean, that would, the capacitor, the inductor, this capacitor, the inductor at first would resist the charge. So if this had no charge flowing through it at first, it would at first resist the charge. But then it would eventually build up. And this is just entirely closed here. It would just act as a closed wire there. And just eventually current would flow through this. And there would just be the same voltage here as there is here. Right? So if this was always closed, and this was 10 volts, once it settles, once everything settles, this will converge to about 10 volts as well. Right? If this were always open, on the other hand, well, then no current would flow, obviously. And so this load would have 0 volts over it. Kind of a simple case, right? But those are the two extremes. So when this is always open, 0. When it's always closed, it has 10, say. Or just whatever that is. But the interesting case is when this switches on and off very, very rapidly at some duty cycle. And the duty cycle here just means what portion of the time this is closed. So it'll always switch at the same frequency. So you'll always say we switch 10,000 times a second. But the question is, what percentage of the time is this open and what percentage of the time is this closed? So what happens when you're switching very fast here is kind of interesting. What happens is that when it's closed, well, charge builds up in the capacitor. The inductor resists things changing. And just intuitively, what happens is that you reach kind of an equilibrium state here. If this is opening and closing constantly, you reach an equilibrium state where this isn't going to have as high voltage as 10. But because charge builds up in the capacitor and current is the inductor stops current from changing direction, from going on, turning off, these kind of both resist change in what's happening here. And so eventually you'll actually get some voltage over this thing that is somewhere in between 10 and 0. And in fact, in the ideal case, the voltage you see here is just this voltage times the duty cycle of this switch. So the duty cycle we measure between 1 for being always on and 0 being always off. If it's on half the time, this is 0.5. And so if this is 10 volts, this will be 5 volts here that you see over this. This diode here is required because there actually can be a case where if we don't have this, current can start wanting to flow the other way around this thing, and you don't want that. Remember, this capacitor here has positive charge here, negative charge here, supposedly. And so it could be the case that if this is sort of something weird is happening here, you might actually have current flowing this way, which you don't want. So you put this diode in here just to ensure that charge will only flow this way. When this is open, remember, charge can't flip through here, but charge, because of these two elements here, you'll have charge, current rather, flowing around this way. And so we won't get into the details. It really is probably easiest to see exactly why that relationship comes out. You have to kind of do an analysis of looking at what the average voltage has to be in order to keep kind of everything in balance here according to those equations of the capacitor and the inductor. When you make, and essentially you can do it all in kind of a mathematical way. You usually have to make some approximations to even solve this thing mathematically, but you can do that, and it isn't too hard, but we won't go into that here. Just you sort of take it for granted that as you turn this on and off, you get something that's kind of in between the always on and always off state, and what that does is actually drops the voltage on that end. Now, just like with the transformers, there's nothing here in the ideal case that's actually dissipating any power, right? So, I mean, in practice, there will be some resistance to both these things, to the inductor certainly, and to the diode probably. But there's nothing here that actually dissipates power. So, and we're talking DC, so we're not talking about real or reactive power here. We're just DC, so there's just real power. Wouldn't even call it real power. There's just power. So what happens here is that all these elements, they don't burn any power. And so because of that, if you drop the voltage here, you're going to have to increase the current over here too, right? The power of the circuit cannot change. And so if you do drop this voltage down, you have the same effects as you have with an AC transformer, in that this has a higher current flowing through it than you would have flowing through here. Okay. That's the ideal case. In practice, these do have some resistance, so you don't have quite the linear trade-off of voltage and current. You're going to burn some power in this thing. But in the ideal case, you would have this be exactly the same, that the ratio of voltage to current, or the product of voltage and current, have to be the same in both, so the ratio of voltage is the inverse of the ratio of the currents. That's just the same equation I wrote back here several slides ago on transformers. You still have all these equations. This middle one doesn't apply anymore, because that's about number of turns around the wire. That's not how you do it anymore. But this ratio here still holds. And so these are really nice, right? Because we all of a sudden can now do DC-DC conversion just as easily as AC, theoretically. And that's a great thing, because now there's really no good reason that we might want to prefer AC power over DC. I mean, there is a reason. There are other reasons than just that. They'll see the efficiency of these things often. For a same efficiency, they might have to be more expensive, especially at high powers. These switches here are not quite as easy to manufacture as a big magnet if they have to have massive amounts of power going through them. But at least conceptually, we can do the same things we did for AC as we are doing for DC. Sorry, same thing for DC as we did for AC. The buck converter is fairly intuitive, right? Because essentially, all we're doing here is we are kind of just opening and closing a circuit to sort of interpolate between the two extremes, right? So that kind of is intuitive. What's much less intuitive, at least it was for me certainly, is the opposite of this, which is a buck converter, which boosts the voltage. Sorry, the boost converter, which boosts the voltage. The buck converter drops voltage down. And what's a little less intuitive to me is this boost converter, which actually increases voltage. So this is actually doesn't look that different in the diagram, but it does the exact opposite of what we did before. It will boost voltage up. So I won't get into that at all, but essentially what will happen here is that as this switch toggles on and off, if it's always, I can't remember which way it goes now. If it's always on, then the voltage would be the same as this, right? And as you go to always off, actually I can go back to this next time maybe if you want, because I'm forgetting the exact ratio of how things work. But basically, if you have it in one direction, it acts just like an open circuit. So I think that would be when it's off, right? So when it's off, okay. When it's off, it acts like an open circuit, so it's normal. If it's always on, what actually happens here is that charge will keep building and building in this capacitor, and you'll get more and more higher and higher voltage here. And so actually, if this is always off, if this is always on, you will actually eventually get an infinite amount of voltage on this side, because this will essentially, current can flow this way, and it can just keep building up, and because it's maintained by this inductor here that sort of maintains the current flow, and so you will keep building up more and more voltage there and have a higher and higher voltage here. Now in practice, you will just burn this thing out if you left it always closed. So, but by toggling these things on and off, you get a situation where you can interpolate again between theoretically infinite voltage here or the voltage of the actual source itself. This is not going to be tested on this. I just wanted to show you these things. The opposite one does exist too. I'd have to go back and actually study all the equations to remember exactly how this works. But I just want to convey the point that it does exist, and you can, just like you can step up voltage in a transformer, you can also step up voltage in a DC system using this buck or this boost converter here. The best way to see that, honestly, is just to actually implement it in a program and see what it actually does. And that's sort of the easiest way to see that this is in fact why this is in fact boosting voltage. Or do the analysis where you basically make some approximations about small changes in current and see what the steady state has to be in order for voltage and current to balance out in the equation. That's how you do it, but won't worry about that. Okay, so that's all for power electronics. Again, this is not, power electronics are kind of a little bit of an aside in this course because they are kind of small scale things. And the course is really much about the grid and bigger scale things. Now what we're going to get to is power flow, which is much more related to how things work on the grid scale. But I think it's good to know the basics of power electronics, mainly because more and more, at least certainly, there are power electronics and a huge amount of loads that we have, right? So much electronics, so much, I guess that's the main one, really, is anything that needs a DC source you have to convert from. So this is becoming, and also there's becoming more and more transmission of DC power. And so these things are becoming more and more important on the grid scale, both in terms of consumption and in terms of the actual operations again. But we're not gonna cover this in depth. The course is not about power electronics. It's much more about the grid as a whole. And so this is all we'll say about the power electronics side of things. So with that, let's jump. Are there any questions about this? Yeah.
Where can we see the DC transfer system?
The DC transfer system?
Yeah. Where do we?
The transmission, you mean? Like DC grids? Okay. There are, in some cases, so one case that actually is very important is underwater cables. Transmitting power underwater in an AC cable causes big issues with the size, and I forget exactly what happens here, but I think the size of the cable creates a lot of, if you want a big enough cable to transmit a lot of power underwater, I believe that the size of the cable means you actually end up having a lot of parasitic effects on this cable, and I forget exactly how these work, but I think that you get a lot of reactance in this cable that you don't want. So you get a lot of things like reactive power losses. And there might be more than that too. You actually might build up capacitance between different power lines and stuff like this. But I could actually get to that in a second, or get to that next time if you're curious more. But the end of the story is that because of these effects, whatever they are, people often tend to favor DC power for long underwater cables. And as these become more prevalent, certainly, say with offshore wind farms and things like this, right? And just wanting to transmit power to islands, for example, we may want to use more and more DC power. There also are some other really big advantages, just the fact that there is not these issues of reactive power losses, things like this. We don't have to worry about reactive power because it's just it's just DC power. There is no reactive power. That's an advantage too. And there can be all these advantages to systems. So because of this, there actually are some high voltage DC lines that are being assembled across the country because of this. They both have their advantages and disadvantages, right? There's more, oftentimes the converters are more expensive to build these things, but once you build them, you don't have to worry about reactive power. You don't have to really worry about some of these cable effects that you have with long transmission systems. And all these things make people often favor DC systems. There's also the fact that a lot of what we use at the end use is DC. So if we're going to be converting to DC anyway at the end, let's just transmit things as DC. So I'm not an expert on all the advantages and disadvantages of DC systems versus AC systems, but there are pluses and minuses to both. And because of that, there are some efforts to build DC transmission into the grid. Anything else? Okay, so let's move on now to power flow. So these slides cover both power flow and power markets, but we're only going to get to power flow today, and we'll see how far we get also. Hopefully enough to give you the basic idea of the problem at least, and the solution, though maybe not all the details of how we compute the solution. All right, so again, power flow deals with the fundamental question at the grid level in terms of transmitting power, providing electrical power. And that is, how does electricity actually arrive from the generators to our outlets here? And more fundamentally, I guess the question really is, for standard power flow analysis, is if all these generators were producing some amount of power, how would that power actually flow through the grid? Now, I'm using the term power flow somewhat informally here. Current is really what flows, right? Power doesn't flow. Power is the product of voltage and current. But it's the term that's used for this, and so I think you can think of power flowing through the grid as well as you can think of current flowing, with the caveat that when you think of it sort of more formally, power really is this current that's moving through the grid, but also times whatever voltage is at the different nodes in the grid. So that's what I sort of mean fundamentally when I say power flow. But it also just is the colloquial term we use for describing these kind of equations that we actually use to solve the systems. It also has gone in the past by the name load flow. So if you see people talk about load flow, that is the exact same thing. Just there's I guess a big debate about which of these two things are more proper in terms of what's really happening physically. Is it power flowing or is it load that's flowing? And neither of these are really flowing. So there's some terminology here which takes a sec to get used to. But I'm going to use power flow. Just know if you see the term load flow, it's the same thing. And again, so the question is, given these generators, I guess more formally, how much current will flow through these particular transmission lines, but we'll just talk about power flowing through the lines themselves. And the key point here is this is actually a much harder problem than linear circuit analysis. So the nice thing about circuits, AC and DC circuits, like the ones we talked about in the simulation program, all the linear ones, the resistors, inductors, and capacitors at least, is that the solution to these electrical equations, that is determining voltage from current or current from voltage, those are all linear systems. What's going to happen with power is, because power is a product of voltage and current, the solution of these things will require solving nonlinear equations. So we can't just plug in a matrix inverse anymore and solve these things. We have to worry about more complex methods of solving power flow. And there are a bunch of complexities that are introduced by this, which I'll get to throughout this lecture. But the basic example, the basic setup that we have here is what we really have are generators, which are, you can think of as AC power sources, I guess. Again, they're not voltage sources. They're really power sources. They prescribe a power and, well, actually, I take that back. Because remember, generators, we could set both the real power output and the absolute magnitude of the voltage. We couldn't really control the reactive power directly. So you can think of generators actually as things that kind of control both real power, not reactive power though, and absolute voltage, for example. And we'll define that much more formally in a second. And loads, you can think of things that just consume some amount of real power and say some amount of reactive power. So just like in our old circuit diagrams, we have all these things, right? We have some, say, generators, which we can maybe for now just informally think of as voltage sources. We have some loads, which might just be resistive or some inductive load there. And then we have transmission lines. And there are much more complex models of transmission lines. You'll actually talk about one in the homework. But for the simple case, let's just think of a transmission line as having some resistance and some inductance. So they all have some total impedance there, which is the combination of these two things. So it's just a resistor and an inductor in parallel. And actually, oftentimes, the inductance here is significantly larger than the resistance. Just the nature of transmission lines is that long cables of wire, you know, if they're built big enough, they won't have that much resistance, but they do have some inductance in these things. So you will experience some reactive power losses in some sense when you put things over a transmission line. Now, this kind of gets tedious to draw after a while, drawing all these inductors and all these resistors and the generators and grounds and loads. So we're just going to draw it like this. And this is a bus bar diagram, sometimes called, or just called a diagram that, yeah, I think it's called bus bar diagrams. But essentially, they draw the exact same thing as before, just without all that notation there. It is so what you have here is you have your generators as before. We don't indicate that they're grounded to any ground here. That's kind of assumed that there might be one end that's grounded. The other thing is that when we draw this, we actually are assuming that there are three phases of power here, but we're only drawing one of the phases. So just like this, in reality, there would be three copies of this, right? One for each phase. We're only going to draw one of those three phases. And then we're going to leave out the actual inductors and resistances here because every line has some inductance and some resistance. We don't want to draw that symbol every time we draw something. But we will actually specify what those are. The loads are often drawn as sort of triangles, kind of indicating they're taking power out of the system, I guess. And then these big, thick bars are called bus bars. And these are assumed to be essentially a zero resistance and zero impedance line. And so I guess the term bus bar comes from the generators are connected to a big metal bus, their output oftentimes. It sort of fixes their voltage. But really in diagrams, this just means that all these things connected to it. And you might have actually both generators and loads on one bus bar. We'll get to that later. But you can assume that these are like lines, but they have zero resistance and zero impedance. So everything connected there is essentially on the exact same circuit, or on the exact same point in the circuit. And then the lines are, just, like I said, are transmission lines, but they're assumed to have some resistance and some impedance. I guess resistance and reactance for a total impedance. So the point I made before then was that if we're going to think of this circuit in a linear sense, things really are no different than they were before. I mean, it's a different way of drawing this, but it's the exact same type of problem here. So suppose, for example, that we're going to assume everywhere that we know the impedances of the loads and lines. So we know both what the loads are drawing and we know what all the lines' impedances are. So assume we knew that. And also assume that we knew, for example, the currents flowing out of every generator. And the convention will be that loads have negative power or negative current flowing through them. Well, if that was the case, then we could compute all the voltages, corresponding voltages, by just solving our linear system, right? We know from last time, or from a couple times ago, I didn't say how to actually compute these. We'll talk today about how to actually compute these matrices here. But we know that any number of currents here will just be equal to some big matrix Y times the voltages. We saw it actually before more in terms of the other one. We saw that so the voltage was equal to some impedance matrix times the current, but these are equivalent. They're not quite, because actually this matrix is not invertible, but you can come up with this matrix. So you have to specify more than just one, more than just three of these actually. You have to specify another one, and some things are impossible. But essentially, you can construct a linear equation like this, and that lets us either compute voltages from currents or currents from voltages just by plugging it into this system here. So that's fine. And in fact, if we also wanted to know, then, I mean, that's answering one question, right? That's answering the question of what are the voltages and currents at all these buses. That's a good thing to know. But then if we want to actually know how much, say, current is flowing through any line, well, then we can just apply Ohm's law and figure out what the actual current here is. So if we want to know the current flowing from node 1 to node 3, I'll just say node 1 to node 2 because it's what's there, we would just take the fact that the current from 1 to 2, which is equal to the voltage at 1 minus the voltage at 2, over the impedance of this line. Right, over, this is just Ohm's law, V equals I times the impedance. So I equals this voltage difference now times divided by the impedance. So it'd be R, the resistance between these two, plus J times what I guess I'm using X for the reactance there. This in total is the impedance. So this sort of asks, or rather answers, every question we might want to know about this system, right? We know exactly how current's flowing through this system. Even though it's sort of weird, right? Because there are more than one generator here. It might look confusing, but really it isn't. It's just a linear system. And we can solve it by this equation and then this equation. And figure out exactly how current's flowing through every single branch here. Now, the problem, though, what I said in the beginning, is that power is different. In power analysis, we don't actually know what the current out of each generator is, for example, right? When a generator runs, there's no really way to control the current. We can control, directly really control the current that comes out of it. We can control the voltage a little bit by adjusting the voltage of that electromagnet that was spinning in the generator, adjust the absolute voltage, not controlling sort of both the real and reactive components of that voltage, not controlling the imaginary and real components of that voltage, just controlling its absolute magnitude. And we can control the real power that's being output, right? That's just sort of the actual amount of power, mechanical power we put into the system. But what we know, informally speaking, is much more like we know power, right? We don't know what voltage or current is in this setting. And so now we just know the product of these two things, and the equations become much harder to solve. So in a second, I'm going to get to the fact that we actually don't know reactive power for generators, right? We know their voltage magnitude, and we know their real power, which is a little bit different. I'll get to that in a second. But just assume for now that we actually did know the actual complex power at each of these nodes. We know real and reactive power at each of these things, which is, real and reactive power, remember, are the product of voltage and current, where you conjugate the current here. So are there any questions about this? Because this is kind of the fundamental thing, right? All of a sudden, we don't know individually what voltage and current here are. We just know their product. This makes for a much harder system to solve. It sort of seems like it could even be ambiguous. How do you determine what current is and what voltage is? Any questions about that?
You can't put any sensor or measuring?
So you could put sensors on it. If you want to talk about measuring it, you could measure current, certainly. But the question about this is much more predictive rather than, tell me what's happening in the existing system right now. What you want to know is, if I turn on my generators like this, what's going to happen? I don't want to have to run it to find out, right? Because if your constraint is that you can't have too much current flowing over this one line, for example, you don't want to just start turning them on and then wait till the line disintegrates before you find out what's happening. The goal here is actually to predict when you turn on all these different things, what's going to happen. But again, predict it using the laws of physics, not machine learning, as we did in the first few lectures. Because this one you can solve physically, right? Just based on some physical laws. But that's the problem, right? If we just know power, how do we know what's going to happen? How can we find what the current will be for different lines here? Fortunately, it actually isn't that hard, though. We have at our disposal these equations still. So actually, sort of arithmetically, it's not that difficult. And I'm going to write it like this. So I'm going to, in all these cases, write the kth element of power. If you have a system with n different buses, say, the kth bus, the power there, well, that just equals the voltage there times the current there, the conjugate of the current. Keep in mind that whenever I'm writing these things are all complex numbers here. So power is complex, has real and reactive portions. Voltage is complex, right? It has a magnitude and a phase angle. And current is also complex, also with magnitude and a phase angle. So this equation holds at every node, we know. I'm going to write it in a little bit more abbreviated notation. I'm going to write it like this. I'm going to say that S equals diag of V times I conjugate. And what this is saying is that this is actually the same equation there. It's just doing it in vector form for all the different nodes. So the important part here is that diagonal matrix times a vector, that will multiply the corresponding diagonal element of that matrix times the vector. And so this is the same as saying Sk equals Vk Ik conjugate for all k. It's just notational here. You're just transforming this to matrix notation. You can't, in matrix math, say V times I conjugate. The reason why is that this is a n by 1 vector, and this is an n by 1 vector. So you're not allowed to multiply those two together. That was actually another issue in some of the homeworks, that people would just use this product here instead of diagonal matrices, which you need to for these expressions. You also can't, you can say like V transpose I, but that's not what you want, right? You want a vector that's the product of all these things, and this would be actually the sum of all the elements here, too. So you really want to use this notation to do element-wise multiplication with two vectors. Okay? So it's good to actually understand that, because we're going to use that a lot. So just all that's happening here is that we're just constructing a diagonal matrix, and we're using it to scale this one, which is effectively just doing the same thing as multiplying each individual element pairwise. Now remember, this here, just to make sure all our units add up here, right? This is an n by 1 vector. This, the diagonal thing, diag just means you form a diagonal matrix with the items of that vector as a diagonal too. That's in the review notes in linear algebra, so you might want to brush up on that if you hadn't seen that before. But this is an n by n matrix. It's 0 everywhere but it's diagonal. And this is an n by 1 vector. So just checking everything adds up there, right? What you get in the end is in fact n by 1 vector, and you can just verify it that it is in fact, you can write it out element by element and verify that it is in fact just the same thing as this. Okay, so this is a way of writing this thing in vector form, this guy here. Now, well, we also know, I guess I erased it before, but we also know that, let me erase this. We also know that the current, well, that just equals this admittance matrix Y, and we'll talk in a second about how you actually form this, but this is the admittance matrix it's called. It's sort of the somewhat inverse of the impedance matrix. Again, modulo the fact that these aren't actually invertible. So this is called the admittance matrix. Admittance matrix. And we know this thing also holds here. Is there 1 or 2 D's in admittance? I think I had it in the last slide. I don't say what it is. Well, I'll say it in a second what it is. I'll figure out if I'm spelling this right or not. So we know this holds here. So we can just replace that with this. Also, conjugation. I'm going to use the little star for a matrix for element-wise conjugation. This also sometimes means conjugate transpose. So you conjugate the elements and transpose the matrix. For technical reasons, sometimes it means one thing, sometimes it means the other. I'm going to always use it in terms of element-wise conjugation, which is actually the less common one. But the way to do that in MATLAB would be, for example, to say so if you have y conjugate here and v conjugate, that would just be, I think it's conjugate of y. That takes the element-wise conjugation in MATLAB. But anyway, that's sort of just a note for when you're implementing your stuff. So conjugation actually is distributive over multiplication and over addition. So if the conjugate of this thing equals the conjugate of each of these times each other, just as a fact. You can prove it very easily. But that lets us plug into this equation now. The fact, well, this now equals diag v y conjugate times v conjugate. Okay, and the cool thing now is we've removed currents from the equation. Right? So now, well, we know the powers, say. We don't know voltages, but this is just n different equations. N complex equations, but still just n different equations. Let's just find the voltages that, in fact, make this true, make this hold. The only problem is that this is nonlinear, right? Voltage appears twice in this situation. So we can't just invert a matrix to find this anymore. However, you already know a way of solving nonlinear equations, right? That was Newton's method. We can use Newton's method to find solutions to this equation. Now, the nonlinearity does more than just make it harder to solve it. It also can make it, there can be situations when it essentially has no solution, or where there are multiple solutions to it. These can all happen for nonlinear equations. But for our purposes, for a lot of systems, it'll actually work very well if you start from some initial reasonable guess of what these things may be. Say voltages are all constant everywhere when you first start off. And if you just then run Newton's method to solve this, to find this thing, then you'll end up doing pretty well. And you'll get a good solution, oftentimes. So that's the basic idea. We don't know voltages, we don't know currents, but we know power. We're going to write voltage as a nonlinear expression of power, and then use Newton's method to find solutions to this equation, to this nonlinear equation. And that's the basic idea of power flow analysis. I should say it's standard power flow. There's also something called optimal power flow, which we'll get to later, which is about optimization with constraints like this. But power flow by itself just means solving these equations. Now, there are a couple problems to this before we talk about how you solve this with Newton's method. And by the way, when I say solve this with Newton's method, remember, Newton's method takes a function, some function of z, and finds, so I'll just write it like this. Takes a function, and it finds, say, z star, such that f of z star equals 0. Right? That's how we defined Newton's method before. But just to see this is sort of how this applies to this, what we have here is, remember, we know this, so our variable is f, our variable is v. And so we'll define f of v just to be the difference between these two things. So f of v is just going to equal diag v y conjugate v conjugate minus s. And so a 0 of this function is obviously a situation where this is in fact equal. Just making it clear how Newton's method for finding zeros translates into a method for solving this equation. Right, so if you find v such that this thing equals 0, then you found v such that this equation holds. Okay, are there any questions about sort of the basic concepts here? We'll delve into the specifics now, but just the basic ideas here. Does this all make sense? Okay, you're going to be implementing this soon, so do ask questions now. If I guess not for the next homework, but not for this homework, for the next homework, you'll be solving this. So do ask questions if it doesn't make sense. Yeah?
Or the reason why we picked conjugates, was that back in the earlier?
Yeah, so the expression for power was just that complex power, S, equals the conjugate of current times the voltage. And I mentioned I talked a little bit about in class about why that expression holds. It's sort of so you cancel out kind of the element of time if you write these as sort of time-based things here, and it basically means that you just get one complex number that doesn't have to worry about sort of a frequency or a time. But that's just the expression. We're just going to take that as a definition of what complex power is, kind of. Okay. All right. I'll leave this up here for now. Actually, no need to erase it. All right. So now that was kind of giving you the main idea. Remember, you know power, don't know voltage. I'm going to go back and mention to you, oh, by the way, we don't really know power either, right? So there's a few problems here. The first problem is that assuming it's reasonable to assume we can know power for loads, for example. Power flow analysis here is going to assume that we do know what the loads are. Remember, this is sort of a hypothetical solution of, if we turn on these generators for these loads, how is power going to flow? So we assume that we will know the loads. Now, in reality, you're going to want to predict those loads. You're going to want to forecast them with things like the machine learning stuff we talked about before. But let's just assume that we know what the loads are. Also, later on, when we talk about optimal power flow, with things like demand response, you might have the ability to actually change what loads are. So you can actually adjust both the generators and loads in your system. But for now, for power flow, we're going to assume that both the generation is fixed and the load is fixed. And we're just trying to figure out how current flows through the network, or how power flows through this network. The intermediate step, of course, is going to be determining what these voltages are. Because once you know the voltages, you can go back and find the currents easily through those equations we saw before. So it's reasonable to say that we know what the total S is, the complex power, real and reactive, for a load. It's not that reasonable to say we know what the S is for generators. Because again, we don't actually have any way of really controlling directly reactive power in a generator. What we can control is the absolute voltage, the absolute magnitude of the voltage, not the complex and real parts of voltage, but just the absolute magnitude of the voltage. So this is sort of makes it a little trickier then, but really this isn't that much harder, because all we're saying then is to say, well, okay, we're solving for both elements sort of in V here. But we could also just say, well, we know some about V. We know V, or the magnitude of V, for, say, every node that's a generator in our system. And in those elements, we just don't know what the reactive power is here. We know P, but we don't know Q. So the common notation here is that what we do is, for loads, we assume that both real and reactive power are known. And those are called, therefore, PQ loads, because we know both P and Q, real and reactive power. And for generators, we assume that real power and absolute magnitude of voltage are known. And so these are known as PV generators then. Remember, it's important to note here that voltage is a complex number. Remember, voltage equals, I'm going to write like this. I'm going to write equals the sort of, equals the magnitude of the voltage at some phase angle. I'm going to talk about voltage largely in terms of this polar form. So we're going to write this. We can also write voltage as A plus JB. But I'm not going to write it this way. I'm going to think of voltage largely in terms of the polar forms. So what we know here is we don't actually know voltage fully. Right? What we know is just the magnitude of the voltage. We do not know the phase angle of the voltage. That's part of what we have to figure out. For loads, we want to find out the whole voltage, right? We want to find out both the magnitude and the phase angle, because we don't know either. For generators, though, all that we know is the magnitude, and we want to figure out the phase angle. I'm going to have all these on a later slide about what's known and what's unknown, so don't worry about it too much just now. I just want to try to give you an idea that you have to remember that these are all complex quantities here. And we're typically going to write power in this rectangular form. So we think of power as being equal to P plus JQ, where we know some of these or some we don't know, and voltage is equal to this thing here, where we know the magnitude for generators, but not the phase angle. OK. So that's the first problem, but it's not really a problem because it's fine. All we're saying is, well, what we really have here is we have two n equations, because we have the equation for the complex side of things and the equation for the real side of things. So we have two n equations, and we have for each of these we have two knowns, or we have these two are being known. So it's really, we're OK still, because we have two n equations and two knowns, two n unknowns, so we can solve it. Again, I will put a slide with all that kind of more rigorously on the next slide, but I just want to try to get the intuition of what's going on here. OK, so that's the first problem, but it's not really a problem. It's just sort of a matter of semantics. We assume some things are known, some things are unknown. And this can be, it's the exact same equation here, where I guess you just would add, instead of just being a solution in V, you'd also solve some elements of P, or some elements of F, and some elements of V. All right. The second problem is that we don't actually know even real power in total. We don't really know what each generator produces or each load consumes. I guess we know what the loads consume, but the problem here is that when you actually solve power flow, you will find that current flows through the network a certain way. This current, unfortunately, creates losses in the lines, right? The lines have some resistance. There's going to be some loss there. So we don't actually know how much loss there's going to be until we've solved the power flow equation. The loss determines how much power you need, so we're kind of at an impasse, right? We don't really know how much power you actually need to provide all those loads. You would think intuitively, sort of naively, that, well, the amount of load or the amount of power produced by the generators has to be the same as the power consumed by the loads. That has to hold, of course, but actually has to be a little bit more power produced by the generators, right? Because there's also power you have to produce, take into account for the fact that there is loss in the lines themselves. And so what we do to solve this problem, and this is a little bit unrealistic here, because this isn't really what happens physically, but we do it because it's a reasonable approximation oftentimes, is that we pick one generator in our system, and we treat it as what's called the slack generator. So this slack generator, for this generator, we don't actually say what its power is. We say your power can be anything you want it to be, so these equations can actually hold here. OK, so for one generator, and just one, we actually won't specify P. We'll specify the voltage still, but we won't specify P. Actually, is this on my next slide too? Yeah, and the other thing that's important is that, well, now we don't have enough knowns and unknowns in our equation, right? Because now we have more unknowns than knowns. But the other thing is that these voltage angles, well, they only really make sense in a relative sense. So voltage angles, there's no absolute zero angle, right? These are sine waves that are oscillating. There's no actual zero. So we're actually going to also say that for this slack generator, we will assume that its voltage angle is 0. So for slack generator, we actually know both these two things. For every other generator, we know these two things. And for the loads, we know those two things. So let me just write that all down on this slide, because you'll probably want to go back to it and refer to it. So OK, here's our final power flow problem. We have n different nodes. And our variables, some of which are known, some of which are unknown, are power, complex power, which is real power plus reactive power, and complex voltage, which we're going to write as, I guess I'll use voltage hat here, VI hat, as the magnitude, and theta I as the angle. One thing with this class is that we are covering several different fields, so there are several different pieces of notation here. Theta here means voltage angle. Theta in the machine learning section meant parameters. There's no real way around this. It's just different fields here have different notations. It's good to be familiar with it. So this is what theta means here in the power systems world. It means voltage angle. But we're going to represent voltage in terms of this polar form. In rectangular form, though, this is just equal to, remember, the voltage magnitude times the cosine of theta I plus j times the sine of theta I. Just to convert between those two things. That's just the definition of this notation here. So these are our variables. Yeah?
When you say there are n nodes,
yes.
Each node is a generator?
Each node is a generator or a load. And in fact, as we'll see in a second, like, some nodes can have both, in which case you treat them usually as generators. They become PV loads because you can still control voltage there. We won't worry too much about that. But some will have both later on, in which case the power, for example, could be the difference between the generated power and the load power. But for now, let's just think about a node being either a generator or a load. And in fact, for the generators, you think of them as PV generators, where you can control, where we know power and voltage, or except this one here where we know voltage and we know the phase angle. So these are our variables. We have 4n total variables here, right? Where we know 2n of them. Okay, so again, for the slack generator, we know the voltage. That's something that we can control at the generator site. So we're going to say that we know that. We know the phase angle, it's 0. Make a little note, maybe that equals 0 there. What we don't know is we don't know how much power it has to generate, because the power it generates will depend on where the power actually flows. So we'll need to change it based on how the power flows. So we'll have to sort of allow this one to provide as much power as you need to supply the network with its losses in some sense. And we don't know reactive power either. For a PV generator, what we know is we know voltage magnitude. Again, we can control that by our electromagnet. And we know now real power. That's basically how hard we push on our turbine, on the crank. What we don't know is we don't know the voltage angle. And that can actually be different from different generators. In fact, it will be different generators. And we don't know the reactive power. Finally, at these PQ loads, what we know is we know power, and we know real power, and we know reactive power. What we don't know is the absolute voltage and the phase angle of the voltage angle. Yeah?
Between two different generators, do you need their phase angles to match up?
No. You do not need that. And in fact, you probably won't have that. Different generators produce different amounts of power, different parts of the grid. Their voltage angles will, in fact, be out of phase often. You just can't do anything about that, because this is not a system where we can actually optimize things, really. All we can do here is just say, well, this is what's known. This is what's ever going to pop out of the equation. And as you'll see, what will often pop out is these are actually quite different. And that sort of is intuitive, right? Because when you have a reactive power, for example, that voltage angle could because you have some inductance in your line, for example, that voltage angle could fall behind the voltage angle of a generator that's sort of not behind that long line with high impedance there. So you will have different voltage angles at different points in the network. And this is actually oftentimes the voltage angles are kind of the most critical thing to grid stability. So we won't talk about this, but if you've ever heard of voltage collapse, or this is actually something that happens when voltage angles get too far out of phase, that essentially these equations stop having solutions, was what mathematically is happening here, and that's really bad for the grid. You don't want that to happen for the grid. You get things collapse. You get, you know, what you would expect to happen, which is the grid collapses. So yes, they are different angles. It's very common for them to be different angles, but you want that to not be too big. Where too big can be 10 degrees, 20 degrees maybe. Getting much bigger than that, you can start to get a little nasty. And in fact, there's a lot of analysis out there on angle stability and sort of showing plots of what angles a system can be stable for and what it can't be stable for, and where in this plot of angles of angle changes your system will start collapsing. So this is all very important, but in general it's fine and common, sort of exactly. I mean, you even kind of want it because difference in voltage angle will also cause current to flow. I mean, you can get current to flow through a line by having different voltages at the different nodes, but you can also get current to flow by having different phase angles at different nodes. That will also cause current to flow over that line, just by the equations of even if the voltages are the same. If their voltage and magnitudes are the same, if they have different voltage angles, therefore you could still have some current flowing through. So it's important that these can in fact and are in fact different. Yeah.
When you say that we don't really know the power of the load or anything.
We know the power of the load. So these are what's known. The load knows its real power and the reactive power.
But you said that like we don't really know the losses on the.
Right. So the powers of the loads we know. We don't know the powers that the lines themselves.
Yeah, but like
use.
Something like we don't really know the powers. What do you mean by that?
What I mean is that the amount of power. So okay, that's a good point. So the power that a line uses is going to be equal to the current in that line squared times the resistance of that line. That's the real power that it uses. So the problem is this equation here, remember I12, this is sort of the power for, and what resistance here is the resistance in the line itself. Remember, I12 equals the voltage at 1 minus the voltage at 2 divided by our, I guess I'm using capital and lowercase, so let me just be consistent here, plus jx12. The problem is our loss here depends on the current flowing through it. This depends, in turn, on the voltages, which we don't know until we solve the problem. So these voltages are unknown at first. Right? We don't know them until we actually solve the power flow equation. So we couldn't possibly know what our losses are on our lines until we actually go ahead and compute the power flow analysis. Remember, this is sort of the key equation here in that once we find all those voltages, we can easily compute all these currents too. But we don't know these voltages yet until we solve power flow. So we don't know what the power losses will be. So we have to have this one generator which certainly can pick up the slack here and which can generate as much power as we need to solve this equation. And what that really boils down to is if we don't do this, if we said let's assume power is known here and the voltage is and the phase angle is known here, well, there actually oftentimes would not be a solution to that equation. There would just be no solution. I mean, this is what can happen with nonlinear equations, right? There's no way you could produce, and it just makes sense too, because if your powers here don't add up to the total power that's being consumed by both the loads and the network, of course there will be no solution to this equation. There's no system that can actually create that. So what has to happen in some sense is that we have to sort of take one node and say, well, we don't really know what the power is there. at a generator, that is.
So like the rest of them, you know the power, and only one of them you don't know. So
Yes.
they add up, you don't really know them.
Yeah, exactly. So if there were no losses in the network, then you would just say, well, we kind of can know all the powers then, right? Because in that case, well, we'll just say that the total power consumed has to equal the total power being produced. So that's sort of okay. But when we don't know when there is a loss in the network, then we don't really, it's impossible for us to know ahead of time what that slack generator, how much power it needs to produce. Yeah?
So you said the slack generator assumption is not actually what happens physically?
Yes.
So what actually does happen?
Well, what actually happens is that when there isn't enough real power, and this is sort of what I talk about with generators, if there aren't generating enough real power, they will start slowing down, right? Their frequency starts slowing down. If basically they're not generating enough power, they don't have enough torque to actually pick up what's being consumed by everyone, they're going to have to start slowing down. To counteract that, the generators will, of course, have a very tight control loop that maintains their rotational frequency. So sort of what really happens is that everyone kind of works together in some way, depending on how all those control loops interact, to kind of pick up the slack all together, just each one trying to maintain their own frequency. That's what really happens. And so it's really sort of unknown in practice exactly how each of these will do it. The thing is, that's usually a small amount of losses in the lines compared to the losses that there are on the load, or the power is being consumed in the loads. So usually this is still a pretty good approximation to how power will actually flow. There are other models, for example, where you actually you say that we know kind of the base power for all of these, but you add an extra variable, which is some sort of bit of power that they all generate together. So you have sort of a distributed slack system. Now that isn't that realistic either, because who knows if they're all going to generate the same amounts of power all equally. But essentially there are other ways of doing this, but for the purposes of discovering how current flows in this network in the end, this is a pretty good approximation. So that's why we do it. We just assume it's going to happen in one generator and say, for the rest we don't really mind.
So just to repeat, see if I understand, to actually solve for any particular network what was actually happening, you'd have to know the dynamics of how these control loops operate.
I mean, if you really wanted to know, yes, you'd probably have to, because these are dynamical systems. They have, loads come on and turn off. This is all steady state analysis, right? So this is all just saying, given some fixed load, this is just what's happening, period. This is what's going to happen. And this, I mean, depending on what would actually happen, would depend on, well, how do those generators come up to provide that load? This gives you one steady state solution. And there could be others, right? I mean, there could be other situations where things produce different amounts of power here, where the generators produce different amounts of power than what you thought. But this is just given sort of fixed information in steady state that we know about what's going to happen to bring that, how will power flow resulting from that.
Okay.
So actually, what time, are we about out of time here? What time is it?
49.
Okay, so we are out of time. Well, you had one quick question there?
We know PQ of the PQ node.
Yes.
From their impedance?
Yeah, I mean, so in reality, again, this is the kind of thing you might want to actually measure. You don't really know it. And what's really happening is it's a big dynamical system where generators just react to it. We're assuming for power flow analysis that we do know it. And we know it just based on, say, our machine learning prediction about what people are going to consume. We can do a similar one for reactive power, certainly. So this is much more for kind of planning stages than it is for operation. Because in operation, these are dynamical systems. You have to just sort of crank them up to do it. This is about how do you kind of understand what's going to happen to schedule what's going to happen with power in some sense. And they're going to use this for things like markets and stuff like that. So yes, we're going to assume that we know these from someone that tells us exactly what everyone's going to consume. And this is also, these are more at the grid levels. This is more like a whole substation will consume this much. Not a individual home will consume this much. We're talking about loads here much more in terms of a substation which then goes to a bunch of different homes. But in aggregate, these are actually not a bad assumption that we can predict these pretty well. All right, so we're going to end for today. Next time we'll talk about how do we actually go about using Newton's method to solve this equation, which is straightforward because you know how to do it in theory, but computing all these Jacobians that you need to do that can be a little bit tricky. So we'll go through that, and then you'll implement it on the homework. All right.